M.V. Satyanarayana of the Department of Physics, IIT Madras. Today's topic for discussion is systems of particles and rotational motion. Let me write the title, topic systems of particles and rotational motion. At the 11th standard and 12th standard level in the CBSE curriculum, with respect to physics, usually one starts with units and dimensions, then motion in a straight line, then motion in 2 dimensions, then you discuss certain important concepts like work, power, energy, and after that one goes towards this very important topic, systems of particles and rotational motion. Let me give now the motivation for studying this, and one studies in the beginning the motion of point particles. Even if one has extended objects like a football, you study in kinematics, you assume that this football is represented by a point particle. A motion of a car, the car is represented by a point particle, but you know it is not going to be tenable at a certain level. The reason is very obvious. We cannot rather neglect the size of the actual objects. Now motion of a solid sphere, motion of a solid cylinder, or we can think about I will give you an important example corresponding to motion of systems of particles. It is very customary for us, when you look into the sky on a nice evening, you will see a group of birds flying. This group of birds will be like this, they will have in different shapes for that matter, but as the birds keep moving, the shape of this contour also keeps changing. And suppose we empty a glass of water on floor, then the water flows. The flow of water is nothing but the motion of water molecules. There are billions of them, trillions of them. Therefore the study of system of particles becomes important. When we consider a cylinder, we will come to it, very solid cylinder, when it rolls, the cylinder consists of several particles. This is also an assemblage of collection of particles, and right. Now each is a collection of particles or assemblage of masses. That is what we call about a rigid body, from a system of particles to, on one hand, like this example, to rigid body. So both these kind of systems can be put into the simple definition of motion of an assemblage of particles. And now what are the various questions which we are going to study? In your earlier lessons you would have seen for that matter that what are the various conservation laws which are involved, conservation of momentum, conservation of energy, conservation of angular momentum, things like that. So one needs to apply these notions, how to extend them, or whether we require some additional notions in the case of systems of particles and a rigid body. And now let me give a simple definition of a rigid body. What is a rigid body? A rigid body is when, for example, you have a metallic sphere and roll it. So the metallic sphere would roll on this table, and each of the particles is also moving, we will come to it. And so in a rigid body what happens, the distance between the linear distance between any 2 points of that object remains constant, it does not vary. On the other hand, if I allow for some amount of water to flow on the floor, the distance between two particles, it is not going to remain same. This is an example of a non-rigid motion, motion of flow of water, and when I leave it on floor. Now there are certain ideal rigid bodies. What is an ideal rigid body? During its motion, its shape remains the same, it does not change at all. On the other hand, if I have a mashed potato and I, depending on the amount of force I apply, the mashed potato will, the shape, its shape gets changed. And so an ideal rigid body is one which does not deform, or the and the change of shape, if at all they are any, they are negligible. And there are two kinds of motion. That is possible for systems of particles or for a rigid body. One, it is what you call it as a translational motion. The translation motion is the simplest. You have already we have already discussed it in the case of motion in 1 dimension, 2 dimensions with respect to point particles. And if I have an ant which is moving on this plane, the ant goes from a particular point A to some other point B. The ant has what we call it as a displacement, right. And now I will give you another example. This is very standard. Suppose I have a wheel. This is very this happens in our day to day life. This is what we call it as slipping. Another name, which another terminology which we use in this country is skidding. It is a common experience in Indian roads on a two wheeler or a cycle. When you move on roads, at certain points, we will not be knowing some oil would have been spilt. So when your vehicle moves on it, till the vehicle reaches that particular point, actually the wheel would be rotating about an axis and moving. It has got both rotational motion and translational motion. But however, when it reaches that slippery surface, what happens is after that the wheel moves like this in a straight. This is what you call it as skidding or slipping. So when this happens, it has only translational motion and rotational motion is not there. This is one of the reasons why when the skidding can be very dangerous, and because the front wheel which enters, suddenly it has only translational motion, and the rear wheel which is yet to enter that particular region which has rotational and translation, therefore it is some kind of a very incommensurate situation, then the vehicle can skid or slip. And okay. Another standard example which you will find in textbooks is I have an inclined plane and I have a, let us say, an object, and this slides. This is what you call it as sliding. Now all the particles of this body have the same velocity v. Remember, velocity is a vector, therefore better you put it there with a symbol. Okay. This is also an example of a translational motion. So all particles have the same velocity at every instant of time. This must be kept in mind. The next example is, suppose I have the same inclined plane, but I keep a sphere on it. It makes an angle inclined plane. That is not important for us now in this study of this. Now if I take a point here, this is the center of the sphere. So if I take a point here, the velocity is like this. This is the direction of velocity. If I take a point here, the velocity is like this. If I take a point here, velocity is like this. Whereas the center of this sphere, which we will call it as a center of mass, we are coming to it in a minute, it will have a motion like this. So the different points on this sphere, suppose I take an inner one, it will have a different direction. The different points of this sphere have different velocity. Now with respect to this point of contact, this is has got it is at rest. So, it is the point of contact, at the point of contact, if you calculate the instantaneous velocity, it is 0. So, different points have different velocities. And now we come to rotation. So, I have been trying to give you motivation for systems of particles and different kinds of motion, which is different from, which will not have that kind of situations in linear motion of a point particles. And I consider the motion of a top. This is very standard, a top. What you do, the top is an object like this. What you do is, it is made of a wood or different material, then you wind around it a thick thread, rope rather, and then you twirl it, then it begins to rotate. There is an axis about which this top begins to rotate. It is an example of a rotational motion. Now, when we consider the motion, this kind of rotational motion of a top, we need to extend all those concepts which we studied in the case of linear motion of a point particle, and then see how well they work. And then rotation of rigid body about a fixed axis. About a fixed axis, that is one axis is fixed. So, I have a rigid body, sorry, I draw a better diagram. So, it is rotating about an axis. Now, you will find that all the points on this axis, they are at rest, whereas different points, if I take a point like this, I will call this as R1, then it is having a motion like this, its motion will be like this. Now, I consider a smaller one, its radius is small, then its motion will be like this, its radius is R2, right. Therefore, the different points on this rigid body, they are having different linear velocities, and they go around, right. However, all the points on the axis are fixed. So, this is what you call it as, these planes are perpendicular to this plane, and this plane are perpendicular to the axis of rotation. Now, you may ask me, sir, is it the only way in which a top would rotate about a fixed axis? Is this point going to be fixed always? From our practical experience, we would have seen we will have slightly complicated motion than motion about a fixed axis, and examples we have considered here. So, I can have a situation, this is from our common experience. What happens is the top, it is little so the original axis was like this, let us say, I will call this as the original axis. I call this as the original axis, I have this original axis here. Now, originally it was very vertical, initially the top was vertical, then it slides and then it goes round, it wobbles its head, then you will have a you have what you call it as, you have actually a cone being generated, right. This kind of motion is what is known as precision. You say that axis of the top precedes about the vertical line, this is known as precision. There can be a little more complicated objects also. Now, let us consider an example of a situation where both are there. Suppose I have a football, we all would have played football at some time or other. I kick a football like this, I have a football, it all depends on the point of application, right. I when I kick this, what happens is even though what I am having is an unlikely instance, the ball as it is goes without rotating about any axis. The ball bodily on its own it moves and comes, even though this is kind of a rotation is this kind of motion is somewhat very rarely happens. This is what we call it as pure translation. This football when I kicked it, it does not rotate about any axis in whatever way, this is pure translation. On the other hand, I can have a situation wherein the way I kick it, it depends, it keeps rotating the ball in its along its trajectory, it keeps rotating about in all possible ways. There may be, it may rotate about one fixed axis or it may rotate about two axes or whatsoever. You would have seen very often when in a football match people kick the ball, it has a very aesthetic trajectory, especially during free kicks, and so and you can see that the ball rotates in its motion when it reaches its final destination. Now so far in the last 10 minutes 10-15 minutes also I have been giving you a motivation for different kinds of motion. One is translational motion, another is rotational motion. You can have rotation about a fixed axis here, you have more complex objects, rigid objects which can rotate about two or more one or more axis, we will come to it little later. And now I will give you one a simple example. Suppose I have a door like this, there are hinges, there is one hinge upwards, there is one hinge here in the lower portion. Now when I this is the floor. Now how do we rotate a door? Very often you have to apply the force normal to it, I indicate it like this, the force is applied in normal way, that is the easiest way to close or open a door. On the other hand, if one were to apply the force at the hinges, the door is not going to rotate at all, you cannot open it, you cannot close it. You can do so here applying a normal force or some force which is making an angle to the door, whichever way. You will find that among all possible such forces, if you apply normal forces normal to the door, which is which makes our life easier to open or close. So it tells you that the rotation is really about the point of action of a point of application of a force, where you apply becomes very important. You may say that I have missed out a standard example like fan, when you put the switch on, the blades of the fan they rotate. There are you would have seen even pedestal fans. In a pedestal fan what happens, a fan would rotate, it has a and then from here what you do, you have here a head down here, so it can also rotate. Once this blade rotates, the blades rotate and you get the air, and it has got an oscillation, and then this oscillation is done. So this moves and provides air to in its range. Okay, there are different kinds of motion are possible. Now now I am going to introduce next one important concept, which is called the center of mass. In the case of motion of a particle moving on a one dimensions or two dimensions, the mass of the particle is a very important notion we need, without that we can't do anything further, either that or momentum. Now we have to introduce what is called the center of mass. it is a key concept. Today I am going to introduce center of mass and tell you how to calculate center of mass in various situations. Later tomorrow I will tell you how this actually arises in a very natural way. And let me give you the center of mass definition. I will consider the simplest of several particle systems is 2 particle systems. So I have 2 particles, of masses m1 and m2. This is at a distance of x1 and this is a distance of x2. The center of mass of this system is denoted by capital X. This I will call it as x axis, this I will call it as y axis, even though I do not need it right now. So the center of mass, it is defined as m1 times x1 plus m2 times x2, that divided by total mass of the system. This is the center of mass. Okay, we will see how it is going to arise. Now if m1 is equal to m2, then automatically center of mass is in x1 plus x2 by 2, very elementary simple calculation you have to do. So 2 objects are there, this is at m1 which is located at x1 with respect to a coordinate system, a mass m2 located at x2 with respect to the same coordinate system, then its center of mass is the middle of x1 plus x2, right. Now we will extend this to several particles. Extending this to several particles, what is that we have? So I have along the same straight line I can take m1 located at x1, m2 located at x2 with respect to a coordinate system. Please, I am not indicating, anyway here I will do it. Then similarly mn xn, then x center of mass, the center of mass is located at m1 x1 plus m2 x2, then mn xn, that divided by sum of the masses, which is nothing but the total masses. We should write these things in an elegant way. It is written like this: summation mi xi, I runs from 1 to little n, divided by sum of all masses I running from 1 to n. This is the center of mass. Okay. Now what happens in the case of in space? What I mean is that this is, we are considering all the particles are on a straight line and then our coordinate system is, center of the coordinate system is here, with respect to that we are measuring distances. Your particles can actually be distributed in space. Then what do we do? I hope you are aware of the concept of position vector. This is what you call a position vector. So a position vector has got, it is x component plus y component plus z component, this divided by, this is how you denote the position vector of a particle. So sometimes we also have this notation, the unit vectors are denoted by Ex, Ey and Ez. So this should not confuse you when we use different kind of, this is also very standard. Okay, in that situation that we write is equal to Xex plus Yey plus z times the unit vector along z direction. This is the concept of position vector. So now we have particles m1 its position vector is r1 and another particle m2 mass and it is at a position vector rn etc. Like this you have, and then you have a situation, this is the rn r sub n unit vector corresponding to the nth particle. Then its center of mass is given by, then its center of mass is a vector quantity. What is that you are going to do? You are going to let me write it then explain. Mi Ri mass into the position vector of the corresponding particle sum over this, that divided by some mi. This is what. Now this is a vector quantity, therefore or I must write a vector for sure, then denote this is center of mass. What is that we have done, sir? What we have done is we have done a similar calculation here, what we have done here, and we have done it the same calculation for each of the axis, for the x axis, for y axis and z axis we have done that, that is what we have done. So now you may have a situation wherein this is if the particles are systems of particles. On the other hand, if you have rigid body, what happens? If you have a rigid body, what will, how do we extend this definition of center of mass? So this particular lecture we are more focusing on this particular very specific definition of center of mass, and we will see how to calculate them. Suppose I have here, let us say this is it is like the mass distribution. I have a rod like a scale, meter scale or a foot scale, right. Now I take an element here, this is, let us say this is x, this is x, one dimension therefore, and then the mass, that is, this is the position I xi, I divide this into smaller and smaller, I consider this is xith division. Now the mass that is here is delta m mi, okay, at the position xi. This is same as what we have done earlier. The infinitesimal mass that is available is a small mass, that is m is delta mi. So I need to multiply that times xi summation over all I divided by delta mi. I runs from whatever. This is how the center of mass in one dimension. This is exactly same as what we did earlier. Only thing is at the particular point xi there is a small mass, that is delta mi. So you may say, you may think that here we have denoted there is a point here, there is a line here, this xi actually represents this. If you want you can take it as a center, no problem. So it is a delta mi. Now if number of such divisions becomes very large, infinitely large, now in the limit as capital N tending to infinity, the limit as capital N tending to infinity, what happens? This will go over to m dx divided by integral dmx, sorry, into x dm divided by dm. The limit as capital N tending to infinity, delta m, it will get converted to the differential dm, here this will convert to differential dm. So in 3 dimensions what happens? The same thing, if the mass distribution is there in 3 distribution and 3 dimensions, then our center of mass is equal to integral. You are going to do one such calculation for each of the dimensions, one for x axis, one for y axis, one for z axis, and it is a vector. Therefore no longer it will remain one coordinate alone, therefore it will r dm divided by dm, where r is the position vector of a typical point around which the mass distribution is dm. Okay. So, these are the various cases which I have seen. Now, we will see few illustrations of this concept center of mass, and one typical calculation that is you will find in most of the books is about let us take our solar system, we will take sun earth system. You know, earth belongs to sun in the sense that it goes around it, one of the planets, and I will give the typical numbers. Suppose I have sun here, I do not need a diagram, just for sun, and its mass is 2.0 into 10 to the power of 30 kilograms. These details you can get from standard literature, and then you have earth, it is very small, right here, small compared to sun, its mass is 6.0 into 10 to the power of 24 kilograms. You can see that this is of the order of 10 to the power of 30, this is of the order of 10 to the power of 24, therefore 6 orders higher the mass of the sun, right. Now, in between distance is 1.5 into 10 to the power of 11 meters from the center of sun to center of the earth, and these values you can get from standard tables. Now, we want to calculate the center of mass of this system. Now, what we will do, we need to choose a coordinate system. I am going to choose the center of the sun. So, center of the coordinate system, x center of mass, choose the origin, choose the center of sun as the origin. Okay. Then if I do that, what will I have? I will have mass of sun into, I have to multiply by the corresponding distance. It is located here. I am now, what I am considering is entire mass of the sun is located here, therefore that is 0 plus mass of the earth times the in between distance 1.5 into 10 to the power of 11 meters, that divided by total masses 6.2 into 10 to the power of 24 kilograms plus other one is 2.0 into 10 to the power of 30 kilograms. This is corresponding to the mass of the earth, this corresponds to mass of the sun. So, I need to substitute for the mass of the earth here 6.0 10 to the power of 24, and you can do the calculation, it will turn out to be 4.5 into 10 to the power of 5 meters. Now, we are getting some number. How did we get this? We are using the definition of standard definition of center of mass, and we are getting a number. Now, we need to compare how big is this or how small is this. So, one way is to look at the radii of sun and earth respectively. What is the radius of sun? The radius of sun is this is the symbol. The radius of sun is given by 7.0 into 10 to the power of 8 meters. You can see that this is of the center of mass is located from the sun at a distance of 4.5 10 to the power of 5. This is the x center of mass. It is not lying here or here or here or inside the earth. The center of mass lies well within the sun at a distance of 10 to the order of 10 to the power of 5. This much distance is what, 10 to the power of 3, 7 into 10 to the power of 8. Therefore, this is much less than the radius of sun. Okay, one need not get shocked about it, we are not inside the sun, only the center of mass of the system is inside the sun. Now you may say, is it always the case, sir, whenever we have two bigger planets? It need not be. The point is, it all depends on how dense is the mass of the sun, what is the mass distribution here. Suppose the same amount of mass is located in a distance of 3 into 10 to the power of 3 meters. Suppose in some other situation where the same amount of mass is located within a smaller radius, then obviously the center of mass is going to lie outside, it will not lie inside the sun, it will lie outside it, it will lie on somewhere here. And so the center of mass is a statement about, it is also a, so we can come to the conclusion that center of mass is also a statement about how massive is when we are dealing in a particular case problem. Now I will consider one more example. You can do the similar calculation in the case of earth moon system. Now I will take a two dimensional example. This is example 1. I will consider another example. In this example I will consider two dimensional problem. I will consider 4 particles. I hope I will draw a nice diagram, looks fine, x axis, y axis. So they are on the vertices of a square, 4 masses. So this I put here 1 kilogram, this coordinate is 1 comma minus 1 comma 1, sorry, this coordinate is minus 1 comma 1, and this is 2 kilograms, I put it here, and the mass is 1 comma, here the coordinate is 1 comma 1. Now here it is 1 kilogram. What are the coordinates of this? X axis 1, y axis minus 1. Here I place a mass of 2 kilograms. What are the coordinates of this? X is minus 1, y is minus 1. Therefore, the center of mass, what is the definition? We need to apply straight away the definition. The mass 1 kilogram multiplied by the position vector is actually 1 comma 1. What is the meaning of minus 1 comma 1? Minus 1 comma 1, it actually represents the vector minus 1 into unit vector I plus 1 into unit vector j. So this is nothing but minus I plus j. So do not get confused that how this denotes a vector. This is another way of denoting this vector which you would have learnt. Then here it is 2 kilograms into 1 comma 1 plus, come to this vertex 1 kilogram into 1 comma minus 1 plus, here it is 2 kilograms into minus 1 comma minus 1 divided by, I have to add all the masses, so 4, 6. Okay. So what will happen to it? You will see here this 1 into minus 1 is minus 1, 1 into 1 plus 1, and then here it is 2 kilograms, I need not write, just I am not writing the units here, plus 2 minus 2, therefore it will be x coordinate is 0, similarly y coordinate is 0. So therefore in this case the center of mass, the R center of mass is at the origin, right. This is how you will be doing these various problems. We can also I can consider this as a lamina and do it. What do I do it? No, now I am doing the other problem. So I am shading this. Here the mass is 1 kilogram, here the mass is 2 kilograms, here the mass is 1 kilogram, and here the mass is 2 kilograms. I am doing the next example. Then what I need to do, the center of mass, this lamina is actually divided into 4 parts. So I take this particular lamina, its center of mass, I will look for a different colored chalk around. Yeah. Now the center of mass of this square is this is half, comma, this will be again half, because the side of each square is half. So like this, so I can find the center of mass of each of the squares and do the similar calculation, okay, fine. Now there are some problems in center of mass which we can do by inspection. What I mean is, there is an inherent symmetry, we can exploit it. We will do 1 or 2 problems, illustrations. So let me consider, I have a, this is by center of mass, this is another example, I will say example 4 involving symmetry. Symmetry is a big term in physics, you will come across it very often. Suppose I have a triangular lamina of uniform thickness, okay, I take a uniform cardboard and cut it, I want to find the center of mass. Now in such cases I can make use of symmetry. As I tell you, what I mean is I can make use of the geometry and straight away one can calculate it. What we do is, I divide into smaller and smaller strips of infinitesimally small thickness. So if I take a infinitesimally small thickness, its center of mass is going to be at the center. So next strip I will take, it will be at the center, therefore all the center of masses will lie in this. Is it right? Now I do the similar thing, therefore I will have, this is what is this line corresponding to? The center of mass of such a strip, all of them are right. Therefore now you can find out, if I do this for this side also, I infinitesimally divide and join the center of mass, obviously the center of mass, this point, this center of mass is what we call it as, where all the midpoints of each side, midpoint of each side is joined to the opposite vertex, such a point is known as centroid. So by similarly, when I have a solid sphere, its center of mass is going to be located at the center, solid sphere of uniform mass distribution. I can also have a situation where the mass distribution is uneven in various regions, not like that, it is a uniform, it is a metallic sphere of a uniform distribution of mass, then its center of mass will be at this point. Now there are situations where one needs to make use of integration, you cannot escape that. As a physics student you need to allow, and it is a tool, not very complicated integrations are required. Suppose I have what I will call it as a uniform mass distribution. So I have a rod which is let us say that this is at the dm is the mass which is located at the x times x. So suppose I know that in this k is the linear density corresponding to an infinitesimal distance dx, this is dx, this thickness is there, no, this is dx. The mass that is available here is dm. So this is whatever length I take dx, whatever infinitesimal bit I take, the mass distribution is k times dx, k is some constant, okay. Then I need to calculate the center of mass. The center of mass by definition is nothing but integral at the distance x there is a distribution of mass dm that divided by total mass of the system. This is equal to, I have to integrate from x is equal to 0 this end, this is x is equal to L. This integral is x square by 2, I need to evaluate between 0 to L, which I forgot to write, 0 to L, this divided by total mass is m, let us say. Then this is I can calculate this because dm is k dx, I forgot to write a k here, sorry, because this dm this is dm times dx, dm is k dx, right. And so when I do that, this will become dx. So I have k dx, this will be equal to L squared by 2, k and k will get cancelled, all that I will have is L by 2. Therefore, if I have a rod of uniform thickness, if the mass distribution is uniform, then when I calculate it, the center of mass will be exactly at the center. This is L by 2 point measured from here, right. Now let me summarize what are the various things we have seen. Before I do that, is it possible to say the center of mass of a system lies outside it? Simplest example is a 2 particle system, center of mass is not going to be with x1 or x2, it is a point mass. Suppose I have an object like this, by symmetry arguments I can say that the center of mass, where is it going to lie? It will be somewhere here, it will not lie on this. And this is another standard example which people use it in gymnastics. I will not go about discussing about it. So let me summarize what are the things various we have seen in this. First we started with the motivation that is required to move on from the kind of problems we study in one particles moving in a straight line in 1 dimensions or motion of a particle in 2 dimensions to several particles moving in general in 3 dimensions. And we saw that 2 kinds of motions are possible, one is translational motion, another is rotation. So a general rigid body is one in which the 2 points are fixed, and okay, the motion of general motion of rigid body is one translation followed by rotation. One important concept that is required, we are going to use it, I will tell you how this concept comes tomorrow, but we have given it and used it, is the concept of center of mass. And I also given different examples of rotational motion possible. We have calculated a few illustrations, we have seen sun earth system, then 4 masses which are distributed on the points of a square, then the lamina problem I did not complete it, hopefully you will do it, otherwise tomorrow I will finish the calculations for you. And last one is how you calculate the center of mass using the symmetry that is involved in the problem, and there are situations where the center of mass has to be calculated using integration. So just to remove that fear, I have taken a simple illustration of a 1 dimensional problem where in a small infinitesimal location dx, that mass is that is available is dm. Suppose I know this law, okay, the mass that is available is proportional to dx, it is called linear mass density, then you will find that it is L by 2. You can have some other mass distribution also, then this, if it is going to be mass is more and more distributed away, the center of mass will move away. With this we will stop for today, and tomorrow we shall go further. Tomorrow we will be talking about what are the conservation laws that are required, how the conservation laws which are used in kinematics of 1 and 2 dimensions can be put to use using the center of mass concept in the case of several particles and rigid bodies. Thank you.